So let's look at the power law model then. As we said, one of the limitations of the Bingham plastic model is that it's a straight line projected straight down to the y-axis. And the straight line may fit the pipe flow very well, but when it gets to the annulus, that straight line breaks down. It no longer describes the flow accurately. So someone came up with the power law model. Oswald de Waal, in fact, came up with the power law model, where tau equals k times gamma to the power of n, which is why it's called the power law. Now we've got tau equals the shear stress, usually in dynes per centimetre squared. K, the consistency index, giving you the slope of the line in the same way as the plastic viscosity, or PV, in the Bingham plastic model gives you the slope of the line, because it's k times gamma, so it basically gives you that what the angle of the line is that you're drawing on the graph. And well, gamma is basically your shear rate in per seconds again, and n is the power law index. And n basically describes the degree of non-Newtonian behavior. I'll show you what that means on this following graph. If n equals 1, we've got tau equals k times gamma to the power of n. So gamma to the power of n is gamma to the power of 1, so it's just k times gamma. So that is basically k then would be similar to mu in your Newtonian fluid equation, which is tau equals mu times gamma. So it's tau equals k times gamma, because n is 1, giving you a straight line through the origin. So it perfectly describes a Newtonian fluid when n equals 1. As n becomes less than 1, this, because it's a power law relationship, gamma to the power of something less than 1 makes this curve off the straight line. And the further it, the lower the value of n, the greater the curve, basically, until you end up with like a curve like this, describing, again, the lower shear rates is described by this section of the curve, and then the higher shear rates are more of a straight line. Still a curve, but approximating a straight line. So the power law is actually more able to describe the annular flow behavior and the pipe flow behavior. But one limitation it's got here is what happens when you've got a fluid that actually does have a yield point. Now, one of the things with the Bingham plastic, the yield point was overestimated by 40 to 90%. Here with the power law model, it's totally underestimated, because if it does have a yield point, the power law model has no provision for that. There is no way of adding a yield point in here. So the power law model basically just goes straight through the origin, regardless. It always starts off here and then curves up. Now, n and k in the power law, in the Oswald de Waal power law, are basically the power law index and the consistency index. And they're described by the following equations. Well, n in pipe, n sub p, is n in pipe, equals 3.32 times the log of theta 600 divided by theta 300. And k in pipe is 5.11 times theta 300 divided by 511 to the power of n. I'm not going to explain where these all came from. Just accept that they were derived by this chap, Oswald de Waal, and leave it at that. Now, in the annulus, n sub a equals 0.657 log theta 100 over theta 3. So again, using lower shear rate values here. And k sub a, or k in the annulus, is 5.11 times theta 100 divided by 511 to the power of n. Now, you can see that we're using the higher shear rates for the pipe and the lower shear rates for the annulus, and that's fine. But again, with most software, you don't actually get the opportunity to put the theta 100 and theta 3 in there. Often with software such as Planet and so on, we'd just be putting in PV and YP for your power law, and it would work out N and K using PV and YP, which are derived from theta 600 and theta 300. So there is no low shear rate modeling again. So the curve's going to be slightly off. We already know it's slightly off because it goes through the origin. So it's not describing it particularly well, regardless of whether you use low shear rates or high shear rates. it's still going through the origin of the curve, and there is no yield point for a power law fluid. Now basically, if n equals 1, as I said before, if n is 1, the fluid is Newtonian, and it decreases, the fluid is Newtonian, and as it decreases it becomes non-Newtonian. And K describes the thickness of the fluid, and as K increases, the mud becomes thicker, as in the slope of that line increases. You need more shear stress to increase the shear rate than if it was a thinner fluid where K was less. So the higher K is, the thicker the fluid is. The higher the pressure would be if you're trying to pump the fluid. And the lower N becomes, the more of a curve that fluid exhibits when you're pumping it at lower and higher shear rates. So the power law model is actually a more mathematically complex model in that basically you're raising a value to the power. You're raising your shear rate to the power of N. Okay, so it's slightly more mathematically complex, and it actually more accurately determines the shear stress at low shear rates. So it models the pipe flow, and it gives a slightly better model at the larger area annular flow where you've got lower shear rates. And it actually describes 3 types of fluids. You can describe 3 types of fluids with the power law model. The first one you can describe, as I showed you can describe this perfectly with power law, is a Newtonian fluid. We don't have very many Newtonian fluids being pumped in the oil industry. You do pump water occasionally, but usually it's water with something in it, which makes it more non-Newtonian. If N lies between 0 and 1, then the fluid's non-Newtonian. It's a pseudoplastic fluid, and yes, the power law will describe its behavior. If N is greater than 1, then it will describe a dilatant fluid. So N actually describes how non-Newtonian the fluid is. It describes that, but it starts off at the origin. It starts off at 0 shear rate equals 0 shear stress. So in summary, the power law is actually useful for modelling fluids with no yield stress at 0 shear rate, which isn't a lot of drilling fluids. It generally underestimates the standpipe pressure when you're modelling. It's more accurate for annular fluid behaviour. However, the fact that there's no yield point greatly reduces the accuracy. So also the reliance on PV and YP as inputs in much of the software also limits the performance of the model. So any combination of RPM readings will give different N and K values. So if you use strictly the 300 and 600 readings, you get different N and K than you would if you used the 3 and the 100 readings, or the 3 and the 6 readings. So if you're using different combinations of readings to produce N and K, you'll end up with different curves. So as I showed you, to do it properly, to perform the power law properly, you should be using your 6 and 300 for your pipe flow, and the 100 and the 3 for the annular flow. So you end up with 2 different curves for one fluid. So you're not really fully describing the fluid with one curve.